Swayam Prabha. Digital India. Educated India.
Very good morning to all of you. So, the last 4 classes we will be looking at a new topic, a very important topic for practical engineering applications, which is the turbulent convective heat transfer. Okay. So, although we do not have too much of time, since we were covering other topics most of this semester. So, we will spend at least 4 lecture hours to emphasize the nature of turbulent convective heat transfer, because most of the practical applications that you are all dealing with, I am sure, are turbulent in nature, and I am also sure that many of you are already taking a course on some introduction to turbulence or turbulence modeling, or part of this is already being covered in a fluid mechanics course. Okay. But the approach in heat transfer is very similar, except that for simple applications, simple arguments, we will use certain analogies. And one analogy which we have already shown for the laminar external forced convection is the Reynolds analogy. So, we saw that since the structure of the momentum and energy equations are very similar, so once you get the expression for skin friction coefficient, we can directly derive the expression for Nusselt number using the Reynolds analogy. So, to start with, the simplistic kind of arguments in heat transfer, turbulent heat transfer, state that we can actually use certain analogies like these, like the Reynolds analogy. We can extend these analogies to turbulent flows also. Okay, and reasonable accuracy they give, in a very less time you can get a good prediction of the local Nusselt numbers and things like that, without having to solve them rigorously using computational methods. Okay. So, let us quickly look at the corresponding range of the flow parameters, which will classify the flows as either laminar or turbulent. And as you all know, in the forced convection case, this is the Reynolds number. So, if you look at external flows, okay. So, we use the definition of Reynolds number, say let us say local Reynolds number, and generally if this local Reynolds number is greater than 5 into 10 power 5, this is for the flat plate. So, the flow tends to change from the regular streamlined laminar pattern to a more chaotic turbulent pattern. Okay. So, similarly, if you go to internal flows, so let us say flow through a duct. So, we use the Reynolds number based on the diameter of the duct, and typically if this is greater than say 2300, so the flow is said to be turbulent. And what about the natural convection? So, in natural convection, how do we classify? What will be the parameter? We can either use Grashof number or Rayleigh number. Okay. So, generally people use Rayleigh number, which is the product of Grashof and Prandtl number, and if you take the case of a flat plate or a cavity, an enclosure. So, typical values of Rayleigh number greater than 10 power 7, these are classified. So, this could be a vertical plate or enclosure, cavity. This is the natural convection in a cavity. So, that is why in the project I have asked you to work at Rayleigh numbers less than 10 power 7, okay. So, up to 10 power 6 it is still laminar. Now, what happens if you cross these thresholds, either Reynolds number or Rayleigh number? So, when you put a probe, okay, so typically it could be a hot wire probe which is used to measure the local velocity, instantaneous velocity at a particular point. Suppose you have the flat plate, okay. So, let us say that till certain position where your Reynolds number is less than 10 power 5. So, this is where our Blassier solution and everything is applied, okay. So, now after 5 into 10 power 5 you have a small transition zone in which instabilities will change the pattern of flow, okay. So, once these instabilities start, you will find that now the turbulent region where Reynolds number is greater than 5 into 10 power 5, you will see motions which are definitely not streamlined, and not only that, you will see several structures, several large eddies of all length and time scales, okay. So, large eddies typically and of a definite structure, these are called coherent structures, okay. Now, you can have length scales which are quite disparate, right from order of magnitude to 5 or 6 orders of magnitude difference in the length scales depending on the Reynolds number, okay. So, the smallest eddy will be naturally lying closer to the wall, okay. So, as you go from the turbulent boundary layer edge towards the wall, the size of the eddies will naturally become smaller and smaller, and finally close to the wall the flow will be only laminar, okay. So, essentially near the wall you have the effect of viscosity, which is molecular viscosity, which is predominant as compared to the turbulent motion, and therefore, this will be referred to as the viscous sublayer or laminar sublayer, okay. So, now the action of the wall therefore is to damp the effect of turbulence, okay. So, without the confinement, without the wall, you do not have a laminar sublayer therefore, and you only have a range of scales in turbulent flow. So, in the case of a typical boundary layer profile, the effect of wall is to damp the large scales, and finally the large scales cascade to smaller and smaller eddies, and finally it becomes laminar close to the wall, okay. Now, only in this laminar region you have the significant effect of molecular viscosity. So, outside this it is all turbulent, and the turbulent motion will dictate the velocity profile, temperature profile, and the characteristics of flow field and temperature field, okay. So, the effect of molecular viscosity and thermal conductivity will not be significant outside the viscous sublayer, okay. So, this is a very interesting physical phenomena, mainly because it is very challenging to observe so many length scales, and also we have therefore different regimes, different regions where the effect of the molecular viscosity can be significant, and in other places where it is insignificant, okay. So, now if you therefore look at these structures, so what do we how do we capture these different length scales. So, if you put a probe, for example, let us say a hot wire probe, and try to measure the velocity at a point here. So, how do you see the variation with respect to time? Okay. So, let us plot velocity versus time. So, you might start with some value at time t equal to 0, and then you might see some fluctuations. It could be anything, but you will definitely see a lot of fluctuations like this. It could be periodic, need not be periodic. Okay. Now, this measurement is called the instantaneous velocity. That means this is at a particular point and over a time instant that you keep monitoring continuously, okay, and you do not apply any filter to this. So, whatever comes out to the probe, and if the probe is quite sensitive, you have to be important that pay attention that the probe is sensitive to all the time scales of turbulence, and therefore, it should be able to resolve these fluctuations. Okay. Now, these fluctuations represent that there is inherent turbulence in the flow field. Okay. In a laminar case, you would not see these fluctuations, it will be a constant value at that point in time. Okay. So, initially there could be some unsteadiness, but finally once it reaches a steady state condition, it will not change, but in the turbulent case there is nothing like a true steady state, there will be always an inherent fluctuation that you will observe, and therefore, so this represents the nature of turbulent flow regime. Now, that you can capture this, how do we then post process? So, what we do usually is take an average of these readings. Okay. So, we can classify this entire instantaneous data into an average and a fluctuation about the mean. Okay. So, there we can assume there is a fluctuation which will represent as u prime, it could be positive or negative about the mean, and therefore, we can decompose the instantaneous velocity as a fluctuation which we will represent is an average which will represent by an over bar. Okay. This average can also be a function of time, we will see that, plus you have the fluctuating component. So, this is a simpler way of basically representing the instantaneous velocity, because the instantaneous velocity has too much of data which we may not need. Okay. So, in order to simplify the post process and also solve the equations, we look at the mean velocity and a fluctuation about this mean, and therefore, we assume saying that the instantaneous velocity is equal to sum of the mean and the fluctuation. So, now this mean velocity also can be a function of time depending on that kind of filter that you apply. So, when we say mean velocity here, how do we calculate this mean velocity? This is nothing but integral some time t to t plus delta t u of t dt 1 over delta t. Okay. So, we can do some kind of an averaging. In this case, I have done what is called as a time average. Okay. So, we can average the instantaneous component over a period of time with a certain filter which is delta t here, and we can, if you do this average, you get what is the mean velocity we have represented here. Okay. Now, if you apply the filter carefully enough, for example, if you have an instantaneous velocity something like this, so some kind of waviness which comes in time, but it is periodic and repeatable. So, if you apply the averaging filter carefully, you should be able to construct a pattern which is repeating and periodic. Understand? So, these are not small fluctuations. So, you should distinguish the waviness, which is actually the time variation of the mean velocity, from the fluctuation, which is your RMS velocity or root mean square velocity. So, if you plot the instantaneous velocity here, and if you carefully apply the time filter, okay, such that this time filter is smaller than the waviness. Okay, so, suppose this is your time scale of the unsteadiness. So, your delta t should be definitely smaller than this. If you apply a delta t larger than this time scale, you will be only getting something like this, right. So, it has to be smaller than the waviness time scale, but it should be larger than the fluctuating time scale. Okay. So, these are the time scales of fluctuation which you want to smooth out. So, in order to smoothen the fluctuations, you need to apply a filter which is larger than the fluctuating time scale, but smaller than the time scale of the unsteadiness. Okay. So, if you select that delta t appropriately, then you should be able to reconstruct u mean, which is actually a function of time. So, this is showing that there is a periodic unsteadiness in the flow pattern, the mean flow itself, and this is coming after you apply the appropriate smoothing. And therefore, the correct representation will be to say that an instantaneous velocity can be decomposed into a mean, which is a function of time, okay, plus the fluctuating component. Now, there are different ways of doing this averaging. So, what I have described here is time averaging. You can also do what is called as ensemble average. That means you take certain data at a certain location, you take it, repeat it again, you repeat it again, you repeat it again. So, you have several sets of data, okay, and then do a statistical averaging of all these different repetitions. So, that is called as ensemble averaging. Okay. Anyway, so for the simple cases of, and also considering incompressible flow regime, people say that does not matter whether you take a time averaging or ensemble averaging, they both lead to the same set of equations. Okay. So, we do not have to worry too much about this for incompressible flows. For compressible flows, we do what is called as Favre average. That means we also have to account for the variation of density, okay, with time, and also the fluctuation of density. Whereas in incompressible flow, we assume that density is constant, although there is a turbulence, the turbulence is affecting only the velocity and temperature, not the density. The density as a property is constant, okay, whereas in a compressible flow, the density also has fluctuations. So, therefore, we have to average rho u, for example, in compressible flow, not just u. Okay. So, this is called Favre averaging, which we will not be worrying about here. You can also do what is called as spatial averaging. So, you can use a filter which is not time, but the grid size, for example. So, this is typically done in what is called as large eddy simulations. Okay. So, you use a spatial filter which is actually the grid size, which can resolve the, which can actually resolve the smallest eddy possible. Beyond that, all the smaller eddies have to be modeled. So, you apply typically in LES, the spatial filter is the grid size delta. Okay. So, like this you can talk about different ways of doing this average, but nevertheless after you average, you say that the instantaneous component is therefore a superposition of the mean component and the fluctuating component. So, like this, if you do the averaging, so how should you model or how should you capture all these scales? So, as you can see that these fluctuations are a result of the small eddies. Okay. So, the time scale of these eddies are resulting in these fluctuations. So, therefore, how do you really resolve this? So, for this what we do is generally the most generic case we solve the Navier-Stokes equation as it is, okay, and we should be able to, when you solve Navier-Stokes as it is, meaning there is no analytical solution to that, we only do it numerically, but we use a grid size which can actually resolve all the length scales, length and time scales. Okay, so, this kind of treatment is called direct numerical simulation. So, popularly referred to as the DNS. So, this is the precise, most precise way. That means, we just take whatever Navier-Stokes equation, because they are valid irrespective of whether the flow is laminar or turbulent, and solve them exactly, but the only constraint is how much you can actually physically resolve, numerically you can resolve. Okay. So, that is limited by the grid size, but you should understand that this is not very trivial, because most of the times the ratio of the largest eddy to the smallest eddy can be greater than 10 power 3. Okay. So, the smallest length scale is called the Kolmogorov length scale. The largest length scale could be of almost the size of, for example, here it could be almost comparable to the boundary layer thickness itself. Okay. The smallest length scale is the length scale before which it finally gets dissipated into heat. Okay. So, therefore, this is called the Kolmogorov length scale, and if you plot what is called the energy spectrum. So, usually when you are doing a DNS, the first thing that you are asked to show is the energy spectrum. That means, it tells you how much turbulent length scales, turbulent energy scales have you resolved, okay, with your grid. So, you will be able to show a energy cascade. Okay. So, that shows that the energy is kinetic energy, turbulent kinetic energy is transferred from the largest scales finally to the Kolmogorov scales, okay, and finally that energy is dissipated as heat at the wall due to the viscous dissipation. Finally, all this turbulent momentum coming from the larger eddies is actually handed over to the smaller and smaller eddies, and finally the smallest eddy will dissipate this. There is nothing else to dissipate, take away this energy from the eddy. So, but it dissipates itself into heat due to viscous dissipation effects at the wall. Okay. So, generally when you do a DNS, you plot the energy spectrum and show that you have resolved all the energy scales of turbulence right from the largest scale to the smallest scale, and this length scales can be at least 10 power 3, the ratio of the largest to the smallest length scale. So, that means you should have a grid size which is 3 orders of magnitude difference. So, if you are therefore doing a domain which is 1 meter, the smallest grid size should be of the order of 1 millimeter. Okay. This is an example, right. So, that means you should have enough grids to resolve anything from 1 millimeter all the way to 1 meter, okay. And sometimes it even falls sub millimeter scale, okay, 10 power 4, if it goes 10 power 5 it goes, you are actually resolving micron scale eddies. Okay. So, this becomes a very challenging task, especially in 3 dimensions. This I am talking about in 1 dimension. Okay. If you need resolution in turbulence is inherently 3 dimensional. So, if you are doing a 3 dimensional simulation, then it will be really a humongous task. You are talking about mesh size of 1 billion typically. Okay. So, to do even basic turbulent simulations. So, which will be very computationally challenging. So, therefore, the alternate option is doing some other ways like larger dissimulation, or the more practical method which is called the Reynolds averaging. So, I think what we will do is spend the next lectures only discussing about the practical method, which is the Reynolds, deriving the Reynolds average Navier-Stokes equation, and then how do we find simple solutions to the Reynolds average Navier-Stokes equations. So, now I mean the Reynolds averaging assumes first you decompose your instantaneous velocity into the mean and fluctuating velocity. So, this is called as Reynolds decomposition. So, this is the starting point of deriving the Reynolds averaged Navier-Stokes equation, which is also popularly referred to as the RANS equations. Now, before we do this, we also have to decompose all the flow parameters, not only the velocity, but also what are all the other things in the Navier-Stokes equation. Pressure, for example, and finally in the energy equation we have temperature. You can do the same thing for V velocity also. Okay. We do the Reynolds decomposition for all the flow parameters here by constructing a filter which could be either a time wise filter or an ensemble wise filter, and then we decompose that into a mean and fluctuating component. Now, before we do the derivation, there are certain rules that we have to list down. So, I will just state what are called the rules of averaging. Okay. So, these have to be satisfied when we apply these averaging to the entire Navier-Stokes equation. The first thing is that when you take the average of the fluctuating component, that is you would have a mean here. Now, if you want to find the average of this, what it will be? It will be 0. Okay. So, that is because you take the mean of the instantaneous, that should be the same as the mean velocity itself. So, therefore, the mean of the fluctuating component should be 0. So, you have a positive fluctuation, negative fluctuation. So, when you apply this over, average it over the delta t, it should cancel out. So, that is the first rule, and therefore, what does it tell you? Now, when we apply a mean to a mean, when we average the mean component over the same delta t, it should give back the same mean. So, it does not matter how many times you average the mean component, it still get back the same mean. That means you still apply the same delta t over that. Okay. So, therefore, it does not make any difference to the averaging. Okay. Now, there is a product rule which states that if you take the product of mean and an instantaneous quantity, okay, and then you average this component, you can break this into a mean of the mean, which will be nothing but the mean times the mean of the instantaneous. What is the mean of the instantaneous? It is nothing but the mean again, the mean component. Okay. So, because the instantaneous average is 0, so if you can substitute as u mean plus u prime, okay, so this will be simply u prime, this u bar plus you have u bar u prime, since u prime average is 0, so that will be 0. Okay. So, the fourth rule is the summation rule, which says that if you have, for example, two mean values, you add them and then you take a mean of that, it is the same as taking the summation of two means. Okay. So, that means if you take the sum of two means and again take a mean of that, it will be the same as just the sum of the two means independently. Okay. So, number 5, apply for example mean to the integral. So, that means I am averaging the entire integral of an instantaneous component. So, I have say integral u dx and I want to average this. So, this averaging operation applies only to this u and not to the integral. Okay. So, this can be written as therefore what? So, if I apply the averaging to the instantaneous component, it returns the mean. So, u bar dx. The same thing can be applied to the differentiation operator also. So, if I say d by dx of u and then I apply the mean to this entire thing, it will return d by dx of u bar. Okay. So, now the other component, the other rule is an important rule. It says that if I take for example a product of the mean and the fluctuating component, and if I apply the averaging of this, what do you think will happen? 0, because this can be split as according to the product rule u bar into u prime bar, and since u prime bar is 0, so this should be 0. Okay. So, these are the rules that you have to keep in hand when we start deriving the RANS equation. So, let us quickly go over the derivation part. So, once you apply the rules, it becomes much easier. So, you please write down the 2-dimensional steady state incompressible Navier-Stokes. Including the energy equation. Okay. So, first is the continuity, all in dimensional form, then the x momentum, so we are writing this only for forced convection right now, okay, without the body force term, but later on you can also derive this for the natural convection case. Right. So, now what we will do first is apply the Reynolds decomposition. Okay. So, we can decompose, all these are instantaneous quantities in turbulent flows. Okay. So, we have to therefore do a Reynolds decomposition of the instantaneous quantities, and then we have to average these equations. So, we have to apply the averaging operation over the entire equations. So, then only we get what are called the Reynolds averaged Navier-Stokes equation. Okay. So, can you quickly do that for the continuity equation and tell me what you get? So, I have written down the Reynolds decomposition here. So, you should be able to, so you can write the continuity equation as d by dx of u bar plus u prime d by dy of v bar plus v prime, and now average of this entire equation. So, usually some textbooks follow some conventions. For example, time average is given by an over bar, ensemble average is given by this kind of parenthesis. Okay. So, you write this means it is an ensemble average. Okay. So, if you write like this is time average. So, some textbooks follow this convention. So, now how do you write this? Use the rules of averaging and tell me. So, this will be, so this operator d by dx of u bar plus u prime bar. So, that will be what? D by dx of u bar. So, we can of course write this as like this plus du prime bar by dx plus dv bar by dy plus dv prime bar by dy. So, according to our rule, this is what? This is also 0, right. So, therefore, you have a continuity equation for the mean flow field. So, there is a continuity equation which satisfies the mean velocities, and therefore, there should also be a continuity equation satisfying the fluctuating component, because since you have a continuity equation for the instantaneous flow field and there is a continuity equation satisfying the mean. So, if you substitute back, you can actually write a continuity equation satisfying the fluctuating component also. So, the velocity fluctuations u prime v prime also should satisfy their own continuity equations. Now, please do the same thing for the x momentum equation. Do the Reynolds decomposition and averaging and tell me what are all the terms. So, I will parallelly do it, but you also do it on your own and then verify it. So, therefore, if you look at the right hand side, this is okay, everybody must have written this step. On the right hand side, this will be, this is incompressible. So, there is nothing, there is no averaging operator on the density. So, 1 by rho d by dx of p bar plus p prime bar, p prime bar will be 0. Similarly, if you do the averaging here, this is u bar plus u prime bar. So, u prime bar is also 0. Similarly, here, right. So, therefore, on the right hand side, it is straightforward. What do we have? After averaging the equation, you have dp bar by dx plus d square u bar by dx square plus d square u bar by dy square. So, the instantaneous quantities are now replaced only by the mean quantities. So, let us look at the left hand side, first term. Okay. So, u bar plus u prime into d by dx So, how can we write this? We can split into 4 terms. So, one is u bar d by dx of u bar, averaging operator applied to that, plus you have u bar d by dx of u prime, averaging operator applied to that. Okay, please remember how I am writing it. Okay, so it is very careful. I have not, because we cannot now split the averaging operator separately to this term and this term. Okay, so we have to first multiply these two terms and then apply the averaging operator. You understand it? Okay, it is not simply something like this. So you have this term plus into multiplied by d by dx of this. Okay, there is no rule which says that this can be written as the averaging operator of over this multiplied by d by dx, averaging operator applied over this. Okay, we have separate rules for d by dx and separate rule for the product, not a combined rule. Okay, so therefore we have to first multiply the terms and then apply the individual averaging operator. So now we will go back to the averaging rule which says that we can apply the averaging operation to these independent things. Okay, so now we have two more terms left. One is what? U prime into du bar by dx whole bar, plus we have u prime du prime by dx the whole bar. Okay, so therefore now we can apply the averaging rule. So what it will be for this case? U bar d by dx u bar, which is fine, plus this will be 0. So you have u bar d by dx of u prime bar, which will be 0. So when it comes to this, now we have the last term. Okay, we have u prime bar multiplied by du prime bar by dx, but we do not have an averaging rule for that. Okay, which says that this should be 0. Okay, in fact when you say this can be actually written, if you look at it as d by dx, we will see that u prime and then apply the average. So when you take the product of the fluctuating components, multiply it with it itself with either u prime or u prime v prime and then take the average, this is not 0. You have to be very careful because this is the one which comes as turbulent stresses. So in this case this is non-zero quantity, we will just write it as u prime into du prime by dx. Okay, we can put the averaging there, but that does not matter. So we can actually leave it as it is. Okay, so therefore we can just keep the averaging operator like this. So if you take the second term, we have v d by dy of so what do you think will come out of this second term on the LHS?
V bar dou u bar by dou y.
So we have v bar dou u bar by dou y, that is correct. The mean components will come as they are. Now fluctuating component, when they are multiplied with the derivative of the mean components, they will be gone, and you have another component which is v bar du bar by dy and the mean of this, which will not be 0. Okay. So therefore if you write the combined equation, so on the left hand side, so you have u bar du bar by dx plus v bar du bar by dy. So this looks similar to the instantaneous terms, convective terms, plus additionally you have the term which is u prime du prime by dx averaged plus v prime du prime by dy averaged. The right hand side you have all the mean quantities. So, now we are going to introduce the continuity equation for the fluctuating component, which says that du prime by dx plus dv prime by dy is equal to 0. So, therefore, we can write this as d by dx of u prime bar plus d by dy of u prime v prime bar minus what do you have, d by dx of what do you have, one case you have u prime du prime by dx plus what is the other term, u prime dv prime by dy. Okay, if you take u prime common, then we have actually du prime by dx plus dv prime by dy, which will be satisfying the continuity for the fluctuating component. So, therefore, this will be 0. You understand? So, similarly, I ask you to repeat the same thing for the v momentum also. Okay. So, therefore, from the v momentum what do you get? You have, if you repeat the same averaging exercise, you will have the mean components in the advection term plus you have additional terms. You have u prime v prime bar plus d by dy of v prime bar, the other terms will be 0. On the right hand side you have dp bar by dy plus nu into d square v by dx square. So, all these are mean components. Okay. So, now therefore, we will stop here. So, in the turbulent RANS equations you have similar terms in the advection component as the instantaneous, but they are replaced by the mean quantities. Apart from that you have two additional terms on the left hand side. Okay. So, these are the u prime derivative and u prime v prime derivative. So, if you write the y momentum equation also you get similar derivatives of the product of the fluctuating components. So, these can be actually taken towards the right hand side, okay, and they can be clubbed to the existing shear stresses. The shear stresses are nothing but tau xx, tau xy and so on. Apart from that you also have u prime bar, u prime v prime bar and so on. So, these are called as now turbulent stresses. Okay. So, although the nature of these stresses are originating from the advection term, okay, they are named as turbulent stresses just for the ease of grouping these together. So, they are grouped along with the viscous stresses and then they are called together as the total stress. So, it seems that there is an additional stress which is coming in turbulence, but that is originating from the inertial terms, and that is why when they are taken to the other side they have given a negative sign, okay, because they enhance the momentum. So, they are not in the conventional sense that they are not stresses which impede the flow. So, they are the ones which are actually promoting the exchange of momentum and energy. Therefore, so they have a negative sign because they are originating from the inertial terms. So, these are called as turbulent stresses. So, what I suggest you to do is do the same thing for energy equation also and see what is the Reynolds averaged energy equation. So, tomorrow we will list down all these RANS equations together and then see how we treat these turbulent stresses. Okay. Thank you.